Welcome to Lecture 3 for Chemistry 312. This lecture is on radioactive decay kinetics, and it's in 3 parts. Lecture 3, Radioactive Decay Kinetics, is also presented in Chapter 3 of Modern Nuclear Chemistry and Chapters 4 and 5 of the Nuclear and Radiochemistry textbook. Part 1 covers radioactive decay kinetics, where we're going to go over some basic equations, concepts of the equations. We're going to talk about error that's inherent when one does radioactive decay. So in other words, you can get an understanding of the error in your value from the total counts of your value. We'll talk about term-specific activity. That's an activity per unit mass. And then a correlation between the lifetime and half-life. Here, this figure is an example of half-life, where it takes an amount of time for the amount of a radioactive material to go from a certain amount to 1/2 that amount. So here, there's 20 atoms. After 1 half-life, there's 10. After 2, there's 5. After 3, there's 2.5, etc. We'll talk about the correlation between this half-life and the average lifetime. So for any of these atoms, what's the average lifetime? How long will each one live? And of course, half-life is a fundamental term when we discuss radioactive decay. Part 2 will cover utilization of the equations, natural radiation, and dating. Another concept that's explored a little bit with radioactive decay is shown here with Schrodinger's cat. In this case, Schrodinger's cat, the idea is the cat alive or dead? It's 2 states. And there's a clip here from the cartoon Futurama, which does a good job of explaining Schrodinger's cat. And we will show that clip next.
DNA and career chip, please.
Erwin Schrödinger, huh? What's in the box, Schrödinger?
A cat, some poison, and a cesium atom.
The cat. Is it alive or dead? Alive or dead?
Answer him, fool.
It's a superposition of both states until you open it and collapse the wave function.
Says you.
There's also a lot of drugs in there.
As an introduction to radioactive decay, let's talk about some of the basic concepts. The number of radioactive nuclei that decay in a radioactive sample decreases with time. So over time, we start off with the number of radioactive nuclei. As they decay, well, they may decay to other radioactive nuclei, but eventually there is a change from something that's radioactive to non-radioactive. And for a given decay, where let's say a radioactive isotope decays from something radioactive to something non-radioactive, we see an exponential decrease, that first law relationship that we saw on the previous slides. We also see that this radioactive decay is independent of pressure, temperature, mass action, and its first order. So in other words, the conditions are pretty well defined. Unlike something like chemical kinetics, this decay kinetics is really a first order decay. So there are some differences in terms of electron capture, internal conversion. So for instance, if I have an isotope that decays by electron capture, but there are no electrons on that isotope to capture, it won't decay through that route. The route still exists, it's just that there's no probability of that decay because there's no electrons. When is this relevant? If you're looking at cosmic rays, which could be described as particles, so flying through space, you could have a cosmic ray that's really just an atom accelerated so fast there are no electrons on this. And as a graduate student, I actually looked at this in terms of an isotope of niobium, understanding what was its, if it wasn't decaying by electron capture, what was its positron decay route. And that positron decay route is a much longer half-life than the electron capture. So something else that's about radioactive decay, it's specific for an isotope and it's irreversible. So in a lot of respects, different than chemistry. So an isotope, when it decays, that decay rate, that decay constant, which we show here and we discussed earlier, is consistent. And you don't get a reaction where something will decay by alpha and maybe it goes backwards where it absorbs that alpha. So naturally, you get all these terms. Radioactive decay is pretty specific. Now, the decay of a given radionuclide is random. If I had 100 atoms, just trying to select which atom that was radioactive would decay, that's probabilistic. I could make a bet that within a certain half-life, right, 50% would decay within the half-life, but I couldn't predict which one would decay. Now, I could talk about the lifetime of each given atom, but I can't specifically state which radioactive isotope would decay at a given time. The decay rate is proportional to the amount of the parent isotope, so the decay rate is equal to the decay constant times the radioactive nuclei. So in other words, the counts per second, this decay constant times the number of atoms. So your activity decreases, since this is a constant, this is my activity decreases as the number of my radioactive isotopes decrease. Decay constant is average decay probability per nucleus for a given time. And that's what our decay constant is, log 2 divided by half-life, and we've discussed how to do these calculations in a previous lecture. The next few slides are going to discuss how some of the fundamental equations used in exploring radioactive decay are developed. The probability for disintegration for any sort of radioactive atom in a given time interval is independent of its past and present circumstances. We described this in terms of the conditions that its decay is fundamentally condition independent. So the probability of disintegration really only depends upon the length of your time interval that you're talking about. If it's a time interval is a half-life, the probability of a disintegration is 50%. So the probability of decay here is equal to the decay constant times whatever time interval we're looking at. The probability of it not decaying, well, it's 1 minus that p, right? So 1 minus the decay constant times the time interval. So the probability that an atom will survive n intervals of this delta t, we take this, we expand that equation, 1 minus lambda times delta t to the n, and then we get n delta t, well, that's just equal to our time, right? That's the number of this time units that we're interested in. That's our total time. Therefore, 1 minus lambda times delta t to the n is just equal to 1 minus lambda t divided by n times n. Again, so that's n is the number of intervals, and t is this time. Let's take the limit as n goes to infinity. It's 1 plus x divided by n to the nth. That's just e to the x. If we have 1 minus lambda t divided by n to the nth, well, that equals e to the minus lambda t. This is our limiting value. So this is how we derive the equation, one of the fundamental terms in an equation to talk about radioactive decay. So if we have n initial atoms, we want to know the fraction that's unchanged in time t. We've seen this equation before, where n is the number of atoms remaining at time t. So n divided by n naught is equal to e to the minus lambda t. So we have this important equation that we've already presented, and now we've derived it, where the number of initial atoms times e to the minus lambda t is equal to the number of atoms at times t. Now this could be used for moles, it could be used for mass, it can even be used for activity, since we know that activity equals lambda n. So we could substitute activity for this term, n, in this equation. As I stated earlier, the error in the counts can be found from the number of counts themselves. It's just the square root of the counts. We're going to go over the next few slides how that's derived. So we've already discussed that radioactive decay is a random process. The number of atoms that a sample that will decay in a given time can differ because it's a random process. If we neglecting the same delta t over large time differences, The time difference is on the order of the half-life, because if it's really long, the numbers are going to tend to even out. This is really true for, let's say, a smaller delta t that's not so different than the that's very different than the half-life. So this randomness gets washed out. If I have something that has a half-life of a second and I count it for 100 seconds, every atom in that sample is likely to have decayed because my count time is so much longer than my half-life. Most of the time, that's not true. You may have a half-life of something that's, even if it's on the order of days, you may only count it for minutes, maybe an hour. So your the amount of time that you count something is much shorter. And if I took a sample with a very long half-life, let's say something like uranium-238, and I counted it for 10 minutes, over 10 minutes, the half-life of 4.5 billion years, the amount of atoms that are going to have disappeared are going to be relatively small. But my count rate can vary over that relatively short time. And this is really due to some sort of this binomial distribution of radioactive disintegrations. We can model it that way. It's a reasonable model to describe the decay process. We can bin count, measure the number of occurrences that fall in a bin number. This can be used as a basis of modeling our radioactive decay. The classic binomial distribution is a coin flip, right? So this is an example of binning numbers, having them fall into certain bins. The probability of obtaining X disintegrations in a bin during a time with a short time compared to the half-life is given by this equation, where we have the number of trials n, and p is the probability of an event in that bin. So relatively reasonable equation. We can use that to help us describe and explain radioactive decay. And we have some examples of different binomial distributions shown here. And these are all derived from this equation. As we discussed earlier, the probability of an atom not decaying in time t is this equation. We've already discussed it. It's a fundamental equation. And this equation is related, this e to the minus lambda t, can be expanded out into our probability equation, where the probability is now replaced by e to the minus lambda, 1 minus e to the minus lambda t. N is the number of atoms that survive in this time interval, t, and n naught is the number of initial atoms. So the time interval between disintegrations is listed as t to t plus d. So let's write this probability, pt dt, and our equation now becomes this expansion. We can continue to use binomial distributions to discuss average disintegration rates. We're going to go back to the original equation that was on the 2 slides earlier that we discussed within this section. So we're going to talk about some n number of ensembles or units that bin into a given value as opposed to the initial amount. And we're going to replace X, the probability, with disintegration. So what we're going to say is talk about how many number of disintegrations fall within a certain bin. We're going to expand that equation here. And then the equation we're going to generate, we're going to replace the X with probability with disintegrations. It becomes this equation. So for an average value of disintegrations, we have an average value, which is shown here. We expand upon this equation, which we then show here, and then we solve using a binomial expansion. And I'll just present this result. The solved binomial expansion is shown here. and then differentiate with respect to x, and that value is provided here. So we have this binomial expansion, differentiate with respect to x within this expansion, and now we have this, which again we're using as a way of trying to describe an average disintegration rate, which is this equation here. Using the equation from the previous page, we set x equal to 1, which is for a single trial. This is really the Bernoulli distribution, which you may have seen in previous courses. The equation then becomes this, where again our average disintegration winds up being a function of number and probability. For radioactive decay, the number, the n, number of bins or objects, is the initial amount, and p, this probability, is 1 minus e to the minus lambda t. So we can use an average number of atoms disintegrating in a given time, where m will be this average number of atoms disintegrating in a time t. This can be either this can be measured as counts on a detector. It's not really disintegrations because detectors they don't measure all the counts. So there's a difference between a count rate and a detection, an actual decay, because of the detector efficiency. But we can use that. We can certainly use counts as a stand-in. We get this equation where the average number of atoms disintegrating is equal to n times 1 minus e to the minus lambda t. For a small term where the decay constant times this time is small, we can just make this equation m equals n naught lambda t. And if the disintegration rate is in unit time, the rate is equal to m divided by time. So we take the time out of this side of the equation, and it's just the number of initial atoms times lambda. So a small lambda t means that the count time is short compared to the half-life, and this corresponds to the equation that we had discussed earlier, where activity equals to lambda n. So one can use this information that we've described to evaluate what's an expected standard deviation from the binomial distribution. We use the binomial expansion, as shown here, as we described previously on page 3-6, and we differentiate with respect to x. So we get the conversion of this equation to this equation, set x equal to 1, and p plus p minus 1 equal to 1. The equation then becomes what's shown here. We get the equation from here as we look at the sum. So we get a relationship between the square of the average disintegration rate minus the average disintegration rate. And this variation is defined as this term where we have the square root of our standard deviation, the square of our standard deviation, and we can expand the square of the standard deviation to this term, which comes from the binomial distribution and the averages. So continuing with the expected standard deviation, we have the average number of counts is equal to the number times the probability. This gets expanded. The square of the standard deviation is equal to np times 1 minus p. So the standard deviation is the square root of np times 1 minus p, and we apply that to radioactive decay. Remember where we defined on page 3.3-9 where m is the number of decaying atoms. The number of decaying atoms is equal to n naught 1 minus e to the minus lambda t. So substitute the number of decaying atoms, the number of atoms that have decayed, that have been counted, times e to the minus lambda t. In practice, our lambda t is small for our count time, so it goes to 1, and our standard deviation becomes the square root of the number of counts. The relative error is the inverse of that value. So this is actually pretty important, very useful evaluation. So everything we talked about, it really boils down to this square root of the number of counts is equal to our standard deviation. And it basically says how many counts do we need in order to get reasonable statistics. And here's an example of the number of counts and the error, and then the percent error. So our standard deviation and the relative error from that. So imagine if you had something that had 10 counts per minute and you counted it for a minute, your relative error would be 31%. That's not very good. Go to 100 counts, so 10 minutes, error's 10%. Go to 100 counts, so 1,000, 100, you want to get to 1,000 counts, so 100 minutes, error starts getting around 3%, and then 10,000 counts, the error is 1%. So this gives you an idea of how long you should count and what's a reasonable error. Generally speaking, if you think about doing an experiment, experimental error can be on the order of a couple percent. So getting the number of counts, somewhere between 1,000 and 10,000, usually means that your counting error isn't going to exceed your experimental error. So that's kind of a target area which to shoot for when one does studies with radioactive samples, in which counting the radioactive samples is included as a way of evaluating concentrations. Let's discuss the relationship between activity and counts. When something decays, we discuss the activity of an isotope. It's got, activity equals lambda n. It may have an activity of 10 becquerel. So the question is, if I put that on the detector and I get 10 decays per second, how many of those are going to turn into counts? Because not every decay is observed. The detector is not 100% efficient. So we need to be able to convert counts to decay. For a given detector, its efficiency at detecting the radioactive decay can be determined, and that value is used to convert experimental count rate data to decay rate data. For calculating the activity, the fundamental equations can be used. Activity equals lambda n. Activity initial times e to the minus lambda t is equal to activity at a given time. So we have these relationships. And what we really need to do is, when we talk about the relationship between counts and activity, it's the detector efficiency. The general relationships that one could see are shown here. If we looked at activity as a function of time on a linear scale, we'd get this relationship, the log scale, so a semi-log graph. We get a nice relationship. And the units for activity, I already mentioned becquerel, 1 decay per second. Another unit is the Curie, which is 3.7 times 10 to the 10th decays per second. This is based upon 1 gram of radium-226. 1 gram of radium-226. If I calculated the number of atoms in a gram of radium-226, so 1 divided by 226 times a mole, times the decay constant, which is log 2 divided by the half-life of radium-226, which is 1,600 years. That half-life does need to be converted into seconds. I get an activity of 3.7 times 10 to the 10th decays per second. So a Curie, that unit, is based upon 1 gram of radium-226. Details of this calculation are shown here. For the decay constant, log 2 is divided by the half-life in years, 1,600. There's 365.24 days in a year, 24 hours in a day, 3,600 seconds in an hour. That gives a decay constant of 1.37 times 10 to the minus 11 inverse seconds. The number of atoms of radium-226 in a gram is shown here, where the atomic mass of radium-226 is used, 1 divided by 226 times Avogadro's number, 6.02 times 10 to the 23rd, gives 2.66 times 10 to the 21st atoms of radium-226 in a gram of radium-226. These terms are then used to determine the activity by multiplying the decay constant times the number of atoms. So there are two activity units that are used, the becquerel, decay per second, and the Curie, this 3.7 times 10 to the 10th, decays per second. The equations that we've discussed can be used to help define some of the terms that we're already using. We've already discussed half-life. That's the time it takes for half of something to decay away. We've seen a few of these curves, the relationship if it's log or linear. The half-life, let's define it, it needs to decrease radionuclides by 50%. And there's a relationship between the half-life and the decay constant. If I took the general equation where the number of atoms at a given time t is equal to the number of atoms initial times e to the minus lambda t, I just looked at the ratio. So the time that it takes to get to a half is equal to e to the minus lambda t. So half is equal to e to the minus lambda t. Let's take the natural log of 1/2 is equal to minus lambda times the half-life, because that's the amount of time it takes for this relationship to occur. So, in 1 half-life, this ratio should be 0.5. And then log 2 is equal to lambda times the half-life. And the half-life is equal to log 2 divided by lambda, or lambda is equal to log 2 divided by the half-life, as we already defined. There can be large variations in half-lives for different isotopes. Short half-lives can be effectively measured. Imagine if I had something that had a half-life on the order of many minutes to hours. I could use a detector. I could sit and count the decay of that isotope if it was, 10 minutes, and I measured a sample every 30 seconds. If I measured the decay every 30 seconds, and I bin that, I could plot it on a line like I would have here, and I would get a decay constant. So something that's a short half-life, that's observable experimentally somewhere along this line, all I need to do is get some areas where I can get some change, some statistically significant changes, and I can generate the equation to derive the half-life. If it's a long half-life, and basically the rate isn't going to change over my measurement period, so imagine something with 10,000, 100,000 years, something like on the order of plutonium-239, around 20,000 years. This is based on the decay rate in the sample, so I need to know the total amount of a nuclide in the sample. So if I had some plutonium-239 and I weighed it, and I got N, and I got the activity of that N, well, I could solve for the decay constant, and then when I get the decay constant, I know that the decay constant is equal to log 2 divided by the half-life. I've measured the half-life. An example of doing something like this is with using a potassium salt. You could get potassium chloride. Potassium-40 is a naturally occurring radioactive isotope. One could put that on a gamma detector, look for the potassium-40, understand the efficiency of that potassium-40 peak on that detector in that geometry, and use that weighing the total amount of potassium chloride, knowing the fraction of potassium chloride that's potassium-40, calculate what the half-life is, and you can compare it to the measured value. So as opposed to discussing the half-life of a radionuclide, the amount of time it takes for half of that radionuclide to decay, I can also discuss an average lifetime of a radionuclide. So it's the sum of times of the existence of all atoms divided by the initial number of nuclides. So this average lifetime is equal to this equation here. And I can expand on this. It turns out to be 1 over the decay constant. 1 over the decay constant is equal to 1 over log 2 divided by the half-life. And it turns out that the average isotope has a lifetime on the order of 1.4 times the half-life. So the average lifetime is greater than half the half-life by this factor, and during some sort of time of initial activity, it's reduced to 1 over E of its initial activity. So I can understand the relationships between these two, but when would you want to know the average lifetime? Well, a lot of times it's important if I'm talking about dose, if I want to understand what's going to be the average dose that one would get. You're talking about then you would talk about the average lifetime. Or if I'm doing atom at a time chemistry, which is what I did as a graduate student, if I only have one atom in a solution, half-life doesn't really make sense. And what you talk about is the average lifetime. So what we would do, we'd measure the average lifetime, get an ensemble of atoms together, measuring the average lifetimes, then we can get a half-life from that. But if you think about it, what you're really doing, if an ensemble, a regular experiment where I can measure the half-life, is really having a large enough collection of atoms to measure these individual averages in an ensembled system that allows you to derive something like a half-life as opposed to just a lifetime. This is a summary slide of everything we discussed previously. This slide has the equations one should focus on. We've got a few equations. This n at a given t is equal to n initial e to the minus lambda t, where this is some sort of number of radionuclides, the decay constant, and time. It also works for activity or counts, right? Because they're both related to n, the number of atoms. It could work for mass. It can work for anything that you could connect. If you could talk about a concentration, how the concentration changes, as long as the volume remains the same, but you're decreasing the number of atoms. We also have activity equals lambda n. So the number of atoms times n is equal to activity. So this is becquerel, which is count per second, and curies, which is 3.7 times 10 to the 10th decays per second. So 3.7 times 10 to the 10th becquerels. We also have lifetime, which is the average lifetime of an atom is 1.443 times its half-life. And if you think about it from the decay, half the atoms should decay within the 1 half-life, but within 2 half-lives, 25% should be there. So the average atom is going to live a little bit longer than the half-life. And then finally, the error, where we have m is the number of counts, and this standard deviation is just equal to the square root of the number of counts. And we use this to determine how long we should perform an experiment to get a reasonable count rate so that the error generated from the counts isn't exceeding or driving the experimental error. Let's make some examples with these equations. So a half-life calculation, let's use the number of atoms at a given time is equal to the number initial e to the minus lambda t. All right, so we'll utilize this in terms of activity. We have an initial count rate of 890 becquerel. After 180 minutes, the count rate was found to be 750 becquerel. What's the half-life of the isotope? Well, activity at given time is equal to activity initial e to the minus lambda t. Solve for lambda. We get to lambda, and it's in minutes because we're looking at minutes. We get a value, this value here is equal to 9.5 times 10 to the minus 4 minutes, inverse minutes is equal to lambda log 2, which is equal to log 2 divided by the half-life. So the half-life is equal to log 2 divided by this value. So the half-life is equal to 729.6 minutes. I could also ask you, okay, how would you describe the error in this study? Well, you need some information. If the count was 750 becquerel, well, you need to say how long was it counted and what was the efficiency of the detector. Ideally, you'd like to go somewhere between 1,000 and 10,000 counts. The previous example showed an example of calculating a short-lived isotope, something where you can look at change over a reasonable time. Well, let's take an example of something where the half-life is rather long. So we use activity equal lambda n, and the example is 150 milligrams, so 0.15 grams of curium-248, shown to have an alpha activity listed here, 0.636 millicuries. So what's the half-life? First of all, let's find the activity. I'm giving you the activity in millicuries. You'd like it to put into something like counts per second. So 0.636 times 10 to the minus 3 curies times 3.7 times 10 to the 10th counts or becquerels per curie, counts per second per curie, gives me my activity in counts per second. So 2.57 times 10 to the 7th becquerel. I need to find n. That's pretty straightforward. If I give you the mass and you have, if I give you the mass and I know what the molecular weight is from curium-248, I have Avogadro's number. I can get the number of atoms, which is shown here. And now I set up my equation. And I use the activity equals lambda n, solve for lambda, put this in, I get lambda is equal to 6.46 times 10 to the minus 14th inverse seconds. Solve for the half-life, where lambda is equal to log 2 divided by the half-life. I get this equation, and I get my time unit in seconds because it's inverse seconds. So that is the one thing you need to be aware of, is that you got to keep your time units consistent whenever you do these calculations. Now, the time unit in seconds, that's not really helpful. 1 times 10 to the 13th seconds. So we convert that to minutes, hours, days, years. So the half-life of curium-248 is 3.4 times 10 to the 5th years. We can use, again, activity equals lambda n from an example where we actually do some counting. Let's say you've got a gamma detector, and at 60 keV, the efficiency is 15.5%. What is the expected gamma counts from 75 micromoles of americium-241? Well, I use this information here to get the gamma branch, which is for americium-241.
The gamma efficiency data shown here is from the table of the isotopes and the Lund University site. These data sets include information not only on gamma decay, but other decay routes, and we will describe these data sets in more detail later in the course.
The gamma branch at 60 keV, so 59 right over here, is, I multiply it by 1 times 10 to the minus 5. This is 3.56 times 10 to the 6, so it's 35.9% is my gamma branch.
Unlike the table of the isotope data, the gamma branching values from the Lund University website are already normalized, so the value here is 35.9, which is the same value from the table of the isotopes.
So I need to take my detector efficiency,
which in this example is measured to be 15.5%.
multiply it by the gamma branching. So in other words, for every time americium decays, 35.9% of the time this photon appears. When that photon appears, I only see it in the detector 15.5% of the time. Then I use my lambda n. That's equal to my counts. I put in my half-life.
Using the half-life of 432.7 years and normalizing that to seconds, where there's 3.16 times 10 to the 7th seconds per year, you get a half-life of 1.37 times 10 to the 10th seconds.
I get the seconds, because remember I said the half-life needs to be at the same unit. It's given to you in years. I need to convert it to seconds. I use this seconds half-life to get the decay constant. So I want to find N. I tell you that there's 75 micromoles of the americium. It tells you how many atoms of americium are present. So activity equals lambda N, right, which is this term. Then I still need to multiply it by the gamma efficiency and then the detector efficiency. So activity equals lambda N times the gamma branching ratio times the detector efficiency. But if I put this sample in, I would expect to have 1.3 times 10 to the 8th count per seconds. That's way too many counts. You would saturate your detector. So what this tells you right away is that that concentration is way too high. We're talking orders of magnitude. You'd better go to 75 nanomoles or even picomoles. You can afford to have 1.28 times 10 to the second counts per second. So you have a lot of variability that you can build into the system. Also helps you understand what concentrations are suitable for doing measurements in your experiments. Another term that's often used in radiochemistry is specific activity. And this is the activity of a given amount of radionuclide. So suppose you use activity equals lambda N, but it really defines how much of a mass or a concentration or a given amount of a radionuclide gives off a certain activity. So the specific activity is listed here, SA of radium-226. We've already described that. So 1 gram of radium-226, the half-life here, we go through the calculation, is equal to 3.7 times 10 to the 10th becquerels. Everything is listed here. And this is the definition of a Curie. This shows the calculations that are done to demonstrate that radium-226 is indeed a Curie. And this is an example of a specific activity where a gram of radium is equal to 3.7 times 10 to the 10th becquerels. And you can imagine doing this for a gram of any isotope you're interested in. So if we look at some other isotopes, specific activity, a gram of curium-244, the half-life is 18.1 years. 1 gram, we get so many atoms in a gram from
Atomic mass
of 244 grams per mole times Avogadro's number. We convert the half-life from years into seconds. So we get a decay constant listed here. Activity equals lambda N. 1 gram of curium-244 is 2.99 times 10 to the 12th becquerel. Now we can generalize an equation for specific activity for a gram is just equals to Avogadro's number divided by the isotope mass times this value divided by the half-life in years. It comes out to this value that's shown here. And I've plotted this on a line. And what I want to show you, there's a failure in this, and it has to do with the carbon-14 is an outlier. Here's the data. And why is carbon-14 an outlier? Happens to be the data set that I've chosen. The mass of the actinides are approximate to each other. Carbon-14 is an outlier. Right, so the mass is fundamentally equal to, is moles equivalent for elements of around the same masses. Carbon-14 is 20 times less massive than the actinides, so it's going to be this outlier. A better way of looking at a specific activity would be to actually look at molarity. If one looks at the specific activity in activity per mole, where N is equal to 6.02 times 10 to the 23rd, specific activity, let's do becquerel per mole of iodine-129, listed here. The half-life is shown here. I calculate the specific activity. From the half-life, I get this half-life into seconds because it's 1.5 7 times 10 to the 7th
Years.
I get that into seconds. I get my decay constant, which is 1.4 times 10 to the minus 15. Activity equals this value times Avogadro's number, and I get so many becquerels. So a generalized equation for specific activity of becquerel per mole is listed here, which is just 1.23 times 10 to the 16th divided by the half-life in years. And we get perfect correlation because moles are related to the number of atoms directly, where if I provide a mass, I need to get the molecular weight of that isotope.
Normally, specific activities are provided in activity per gram. You can find that data, but I wanted to provide an example of activity per mole, which demonstrates the real consistency in the calculations.
A final example of a specific activity could be something you make up in the laboratory, which would be a specific activity with a carrier. So imagine I wanted to do something with column chromatography of europium, understanding lanthanide. Maybe I'm trying to recover lanthanides from materials, and I want to see how efficient my separations are, my recovery. What I could do is take some stable europium and spike it with some radioactive europium. So if I took a millimole of europium and I added 1,000,000 becquerels of europium-152, I could count the europium-152 and I could know how much total europium is present. So I could get the specific activity of the europium in becquerels per grams. So how many grams of europium are present? Well, the amount of europium that I'm adding, the mass of the 152 is insignificant compared to the stable europium. So I have 1 times 10 to the minus 3 moles of europium. This is my molecular weight. I have so many grams. And I put in 1,000,000 becquerels divided by so many grams. I get 6.58 times 10 to the 6 becquerels per gram. So now if I counted a sample and I knew the counts, I could use that to determine the grams of europium that I recovered. I could also state, well, if I have 1 times 10 to the minus 6, 1 times 10 to the 6 becquerels divided by 1 times 10 to the minus 3 moles, I get 1 times 10 to the 9th becquerel per mole. So I can also evaluate the europium concentration in terms of moles. What's the specific activity in 5 years? Well, europium-152 has a half-life of 13.54 years. I can plug this into the equation that we talked about. The activity at time t would be equal to the activity initial times e to the minus lambda t. So if I was talking about in terms of becquerels per gram, in 5 years, it would go from 6.58 times 10 to the 6 becquerels per gram to 5.09 times 10 to the 6 becquerels per gram. So you do need to consider any changes in activity that would occur with your carrier and specific activity due to the half-life of the isotope that you're adding. So a final example of a calculation from the equations that we've covered in part 1 of this lecture is the lifetime. And let's look at an example of atom at a time chemistry, Rutherfordium-261. What's the lifetime of this atom? Half-life is around 65 seconds. So 65 times 1.44 is 93 seconds. And this we use to determine the time for an experiment. We would want to perform a separation and get that sample on the detector within 90 seconds so that that would be the same. So you're doing an experiment in the average lifetime of one of the atoms you're producing. So this gives you an idea if you're making short-lived isotopes, so elements that are on the edge of the periodic table and on the end of the heavy elements, which are short-lived, gives you an idea of how much time you need to prepare these samples and perform your entire experiment so that you're not having too many atoms decay as you're preparing the sample. This concludes part 1 of lecture 3, radioactive decay kinetics. When you've completed part 1, please move on to part 2.